So welcome to week 4 of problem solving session for the course control systems. So in the last week we have seen questions on first order systems and stability conditions, etc. And in the course you have gone through lectures on second order system, the time response of second order system, how can we characterize the solution, and some controllers like proportional derivative type of controller. So we will solve questions related to these topics today. So starting with the first question. So here we are given a second order system whose dynamical equation is given as y double dot plus 4y dot plus 2y equals to ut. You have to identify whether this system is underdamped, overdamped, undamped, or critically damped. So we know that we can characterize the system as underdamped, overdamped, or undamped based on the value of zeta. So for this system, we are given y double dot 4y dot plus 2y equals to ut. So if we find out the transfer function, we will get 1 by s squared plus 4s plus 2, very simple. And if we write it in terms of the standard form, we know we have 2 zeta omega n equals to 4 and omega n square equals to 2, right? So from here omega n equals to root 2. So putting that value here, we will get zeta equals to 2 by root 2, which is root 2. So since root 2 is greater than 1, so zeta, so here the system will be overdamped because here zeta is greater than 1. Okay, very simple one. Now here is the second question. For the second order system, identify the natural frequency. So like the previous question, we can proceed in the similar manner. Here also we can easily find out the transfer function, which is s square 6s plus 20. Okay, and here also 2 zeta omega n is 6 and omega n square is 20. So natural frequency is nothing but omega n. Okay, so omega n is under root 20. So under root 20 means, in decimal, what is under root 20? Please calculate. So it is 4.47 radian per second. Okay, very simple one. Now for the same problem, identify the damping ratio. What is the damping ratio of this system? So let me write the system for you here. The system is y by u equals to 1 by s square plus 6s plus 20. Okay, identify the damping ratio. Okay, sorry, my mic was off. So in question number 3, you have to find out the damping ratio. So this is the question number 2, where we have to find out the natural frequency. So we identified it using the standard form. And in the third question, you have to find out the damping ratio of the same system. So I have written the system here. For this system, identify the damping ratio. Okay. Those who are preparing for GATE, try to calculate everything using the calculator given in your laptop, because that way you will be very familiar with the one provided in the examination also. Okay, for this one we know the natural frequency is under root 20. So 2 zeta omega n is the coefficient of s, that is 6. Okay, so omega n, no, we have to find zeta. Okay, so zeta is 3 by omega n, which is 3 by under root 20. So if you calculate it, you will get 0.67 something. So the correct option is third. Now for the same problem, identify the frequency of oscillations in the unit step response. So for this second order system, you are providing a step input, and then you have to identify what is the step response, what is the frequency with which the response oscillates. Okay, so here the transfer function is, okay, this is your system. Identify the frequency of oscillations. Okay, how to solve this question? For this one, we just have calculated the value of damping ratio zeta, right? And we got 0.67. So can you identify which type of system it is? Underdamped, overdamped, critically damped? Now since zeta is less than 1, so it is underdamped system, right? So in case of underdamped system, we can write this solution yt for the step input as, so we will have roots at minus zeta omega n plus minus j omega n under root 1 minus zeta square, right? So, and this we can write as j omega d, right? Omega n under root 1 minus zeta square we write as omega d, because with the effect of damping, the natural frequency is damped frequency, right? So it is given as omega d, and the solution is given as cos omega d t minus zeta, right? You need not to remember this solution, but I just want to convey that for step input for underdamped system, you generally have this form of solution. Now can you identify with which frequency the system will, the response will oscillate if this is the solution? Oscillation is coming from the cosine and sine terms, okay, and these have frequency of,
Omega D.
yes. So what is omega d in our case?
Omega n
So
into
here
1
is the
minus.
system. So for this system, can you find out omega d? So it is under root this value, and omega n we just calculated. What was that? Under root 20, and zeta was 3 under root 20 whole square. Calculate this value. Again, I am saying trying to use the calculator of your laptop or your PC.
3.31.
3.31, yes, approximately it is 3.31 we can write in radian per second. So the answer is fourth one. Okay, this detailed solution you can refer to the lecture of this course, and this is very easy to derive. You have, in case of step input, you will have s square plus 6s plus 20, and this you can also write as 1 by s plus 3 whole square and plus 11, right? You can write this system as this also. Now from here, if you do the partial fraction, you will have some terms as a by s plus something divided by s plus 3 whole square plus 11 plus something divided by s plus 3 whole square plus 11, right? So these terms will give you sine and cosine terms, and here if you see, you have terms like, sorry, some problem. This is not working. Just give me a moment. It's not working. I don't know why. Okay, sorry. So we had terms like s plus 3 square plus 11, and there were other terms also. So these will contribute to cos and sine terms, right? So here also, if you do the inverse Laplace, you generally have e to the, you will get e to minus 3t. If there is some constant, then there will be a, and then you have sine under root 11t, right? Isn't it? Or cos under root 11t, because omega here is under root 11. So if you do under root 11, you will get the same value. Can you check? So in this way also you can verify that the response will oscillate with the frequency 3.31. Okay. Okay. For this system, calculate the rise time. What is the rise time of this system? System is y by u equals to 1 by s square plus 6s plus 20. Calculate the rise time. So what is the rise time of the system? If, let's suppose, I draw the response of the system like this, okay, if this is the final value, can you identify what is the rise time from this graph? Which point will denote the rise time?
Time to reach the steady state value for the first time.
Yes, perfect. So the steady state value in this case is this dotted lines. Okay. So it reached the steady state value for the first time in time tr. Okay. So in the above solution, you can put yt equals to 1 and then you can calculate the time. So for this we have a ready-made formula also, that is given as pi minus beta divided by omega d. Now what is beta? So beta,
Tan inverse omega d by sigma.
yes, for underdamped system we have poles at minus zeta omega n and plus and minus also j omega n under root 1 minus zeta square. So this angle is called beta. Okay. So cos beta is nothing but zeta. So beta is cos inverse of zeta. Okay. Now calculate beta, because zeta we have already calculated for this system. It was, I think, 0.671. Calculate beta. So
No, 47.9.
okay, I'm facing some issue with my pen today. It's not working. Okay, so beta you are getting how much?
47.87.
In radian, what is it?
No, degree.
Calculate in radian, because omega t we are
Ma'am,
given in radian per second.
in radian it is 0.836.
0.836, correct. Then how much rise time will be? mm,
0.7.
0.7. Okay, let's see. It's not working today. Give me a moment. Let me disconnect and I will connect. Give me 1 to 2 minutes. actually my pencil is not working, so now I have to use my fingers to write. Okay, so it was, sorry, cos inverse theta, so it is 0.835, right? And then when you calculate rise time, uh, be sure that you are using the um, you are calculating everything in radian, okay, because omega t is given in radian per second. So if you calculate tr, it will be pi minus 0.835 and divided by 3.316, so this will be around zero point 0.7 second. Okay, so option B, right? Okay, for the same problem, calculate the peak time. Okay, my mic was off. So I was saying that my pencil is not working, so I need to write using my fingers. So for the next question, you have to calculate the peak time for the same system. So what is peak time? So we know for the response of second order system when it is under damped, we can see many peaks, right? Here, and so on, until it goes on to converging to the steady state value. Okay, it will have continued oscillations. So the first peak, the time to reach the first peak is called the peak time. So for this case also, we have a ready-made formula based on the characterization of the solution of system. So the peak time is given as pi by omega d, okay, and omega d, I think we have calculated in previous question, it was 3.316, right? So omega d was 3.316, so TP will be how much?
0.95.
0.95, yes, correct. So it will be 3.14 divided by 3.316, so you will get um, 0.947 second, which is close to 0.95. Okay, simple questions. Calculate the maximum peak overshoot. So how much the overshoot is happening with respect to the steady state value in percentage, you have to calculate. So again, if we draw the response, so this is the peak value, okay. Now this peak with respect to a steady state is this much a, right? and you have to find out the maximum peak overshoot. So it is generally given as in percentage, it is y at t peak minus y at t infinity divided by y at t infinity, right, into 100%. So basically the value a divided by the steady state value. Or the other way, we can calculate using the parameters of the system. Okay, so maximum peak overshoot can be given as zeta 1 minus zeta square. Okay, let us go. Zeta square. Okay, so calculate how much you will get.
I got 5.8.
5.8. Okay, so zeta was, how much was the zeta? It was 0.671. Okay, so it is minus pi into 0.671, 1 minus 0.671 square. So if you calculate, you will get 0.0582. Now if you calculate in percentage, it will be 0.0582 into 100, which is 5.8%. Okay, sometimes you will be given values based on these graphs. So if the question appears like this, you need to calculate the percentage overshoot using this formula. Now calculate the settling time.
No, 1.33.
1.33. So 1.33, it is for 2% band or 4% band?
2% band.
Sorry, or 5% band, 2% band. Okay. So when it is not mentioned in the question, you have to assume that you have to calculate for 2% band. Time to reach around 2% of the steady state value. Okay. So if this is the steady state value, how much time it will take to settle around 2% of this value? Okay, it will stay like this. So again, for 2% we have, or another way we can say 98% of the final value. Okay, so in that case settling time is 4 by zeta omega n. So you can calculate and check which value you are getting. Okay, because these are just calculation based questions. Okay, now in this question, regarding proportional controller, which statement is correct? Read all the 4 statements and identify which one is true. So for proportional controller, we have the transfer function of the proportional controller as only the gain kp. Okay, so the first statement says that the controller transfer function is a first order polynomial in S. So is it true or false?
False. False. It
Yes,
is a constant.
because yes, it is a constant, so there is no polynomial of S. The second is saying it would lead to zero steady state error for all stable closed loop systems while tracking a step reference input. So if you apply a step input, it is saying that you will, and the plant is stable, you will always get a zero steady state error. Is it so?
No.
Yes, because in that case, there will be scaling with respect to this gain. You may not settle to zero steady state error value. Okay, so for step reference input, 1 is the reference value, but you may not settle to 1 because you have this gain kp, right? So this option is also not correct. The third one is control input is inversely proportional to the error. Is there an inverse relation with the error? So if we consider the closed loop system, if this is the controller block, this is the plant, here is the output y, and there is a feedback h. Okay, so this is the reference r t. Now let's suppose h equals to 1, then this will be yt, so plus minus. And here the controller in our case is kp. Okay, so r minus y is nothing but error. Okay, so now can you identify whether the controller is proportional or inversely proportional to error?
Proportional.
Yes, because if this is the output of the controller, let's denote it as C1T. So C1T will be Kp into Et, right? So it is proportional, the output of the controller is proportional to error. So this statement is also not correct. The last option is the control input at an instant of time is dependent only on the value of the error at that time of at that instant of time. So we can easily check from here that the control input, control is function of kp, so control is nothing but kp, and controller is defined as kp, it is acting on the error et. So at a particular instant of time, say at time t1, controller is dependent on e of t1 only, right? At present time only it is dependent, not on past, not on future. Okay, so the control input at an instant of time is dependent only on the value of the error at that instant of time, only the present value. So this option is correct or not correct?
Correct, ma'am.
Yes. Okay, for this system identify whether it is stable, unstable, marginally stable, or what. So how to comment about stability?
We have to find the poles of the transfer function.
Yes, so let's first find out the transfer function. So this will be the transfer function. Now without calculating the poles, by looking at the characteristic polynomial, so the characteristic polynomial is nothing but s square plus s plus 2. Can you comment on the nature of poles? So for a polynomial of order 2, we have this necessary condition that if the coefficients of if all the coefficients, okay, like here we have 1 1 and 2, they are of same sign, they are non-zero and they are of same sign. So here all coefficients are present, okay, for s square, for s1 and for s0. For s square we have 1, s we have 1 and s0 we have 2. So all the coefficients are present and they are of same sign, all are positive, okay. Then what it says that the poles of this characteristic polynomial will lie on the left half plane, okay. So if that is the case, then what can you comment about this system?
It is stable.
It is stable, yes, correct. Now what if you have a third order polynomial like sq plus b s square plus cs plus d? What can we say about this polynomial? Can we generalize it for any nth order polynomial or not? So this is a necessary condition but not a sufficient condition, okay. For second order system we can generalize. For third order system we can say that if the coefficients are non-zero and of same sign, okay, for first and second order, we can say that the poles will lie on LHP, okay. But for higher order, for n greater than equal to 3, if any coefficient is 0 or there is change in sign, then we can say that all the poles will not lie on, at least we can say this, but we cannot say that all poles will lie on LHP, okay. So for second till second order we can generalize, but for n greater than equal to 3, if all the coefficients are present and they are of same sign, we cannot say that all will be on LHP, but what we can at least say, if any of the coefficient is 0 and there is change in sign, then we can say that all poles are not lying on the LHP, right? Okay. So a unity negative feedback closed loop control system. The question visible to all of you? It says that a unity negative feedback closed loop control system is designed with the above plant, okay. Like the transfer function is 1 by s square plus s plus 2. Let me write it for you. Okay, and the controller is a proportional controller, so you have to identify the closed loop system is stable for all kp of what value. Try it yourself.
No, is it positive feedback or negative feedback, ma'am? Please clarify.
Oh, sorry. It is a negative feedback, unity negative feedback. So this we cannot write it as by u. This is the plant transfer function. Okay, so hs in this case is equal to 1 and this is negative feedback. So what will be cs? It will be just kp, right? So gs will be c into p, which is kp by s square plus s plus 2. Okay. हाँ बोलो. नहीं नहीं नहीं. Okay, sorry. So g is kp by s square plus s plus 2. So what will be the closed loop transfer function?
Kp by s square plus s plus 2 plus kp.
Yes, so we can write it as g by 1 plus gh, and h is 1, so it is kp by s square plus s plus 2 divided by 1 plus kp by s square plus s plus 2. So we'll be left with only s square plus s plus 2 plus kp. Okay. Okay, so now using the above logic that I have just explained, can you identify when this closed loop transfer function will be stable? This is the characteristic polynomial s square plus s plus 2 plus kp, okay, equals to 0. So this is a characteristic polynomial. How can we ensure the system will remain stable? If I introduce a proportional controller kp, what should be the value of the constant kp such that the closed loop system will be stable? So for a second order polynomial to have roots on the LHV, what we need to ensure? first condition is all the coefficients should be non-zero. So first we have to ensure that 2 plus kp should not be equal to 0. Okay, then only we have this coefficient, and another condition is that all should have the same sign. So we have all these two coefficients as positive, so we need to have this one also positive. So 2 plus kp should be greater than 0. Okay, so from here we can write kp should be greater than minus 2. Okay, it should not be equal to minus 2. Okay, sometimes you may get option like kp greater than equal to minus 2, because when it will be minus 2 this coefficient will go to 0. Okay, but we need non-zero coefficient, so the correct option is kp greater than minus 2. Okay, so any questions? Okay. For that same question, if a unit step input is given, what will be the steady state error if a step input is given to the system? So we have just now designed the closed loop system, which is given as y by u is kp by s square plus s plus 2 plus kp. Okay, what is the steady state error if u is step input? U is 1 by s. Calculate the steady state error. So if you see from the block diagram, here is the controller, here is the plant, output, feedback is just 1. Okay, this is C, this is P, and we are providing R as a step. Okay, and we have a negative feedback, plus minus, so this will give us error. So if I want to write for error, what can I write? Can I write R minus y? Okay, any problem? So, and y we already know. What is y? Y by u we already know, it is given as this transfer function, which is nothing but g by 1 plus g. Okay, so y is, and u in this case is r is step input or the reference input, so y is gr divided by 1 plus d. Now we can write e as r minus gr divided by 1 plus g. Okay, so what is e? Will be left with r divided by 1 plus g. So this is the error. Okay, so first we need to calculate error. We can calculate easily by putting r as 1 by s, and g we have g is nothing but c into p, which was kp divided by s square plus s plus 2. Okay, so what is e? E is 1 by s into 1 plus kp s square plus s plus 2. Okay, now for steady state error, what we need to do? We can use the final value theorem. What it says?
We have to put s is equal to 0
Yes.
multiplied by
First we
s and
multiply
1.
with s. Yes. So E steady state will be s into E of s limit s tends to 0. So what you will get? You will get s by s 1 plus kp by s square plus s plus 2. So these s will cancel out, and if you put s equals to 0, this will go to 0. So you will have only 2 will go numerator, and this will be kp plus 2. So which option we are getting? 2 by kp plus 2. Option A. Okay, in this way you can calculate the steady state error of the closed loop system driven using the step input. Okay. Okay, you have to identify the true statement. Regarding the integral controller. First, can you tell me the transfer function of the integral controller? How can we represent an integral controller?
Ki by s.
Yes, it is Ki by S. Okay. Now, based on that, try to figure out which one is true. So, first option is saying it can amplify um, low magnitude, high frequency noise. So first thing I can see is this is an integral controller, right? So it will integrate any function given to it. So let's suppose error is somewhat like low magnitude, right? Low magnitude means 0 0.1, and high frequency sine 100t, let's suppose. So if you integrate it, what you will get? Integrate this function only. What will be the integration of this function? It will be nothing but
0.1 cos 100t by 100.
okay, so it will be minus cos 100t, so it will be 0.1 also, and divided by 100. Okay, so is it amplifying it or not? So this is
No, it is further reducing the amplitude.
yes. If there is a high frequency noise, then it is reducing the effect of that noise. Okay, so this option is not correct. Okay, what about second option?
Yes, ma'am, it is true.
It is saying the controller transfer function introduces an open loop pole at 0. Yes, it is correct. We have a pole at s equals to 0, right? So this option is correct so far. What about third one? It would always lead to non-zero steady state error while tracking a step reference input. Is it so?
No, I have no idea, ma'am. Please explain.
Okay, so it is saying that, let's suppose, let's take an example. Okay, let's say we have plant transfer function as 1 by s plus 2. Okay, okay, no, not in that example, we have seen that. Then what will be cs? It will be ki by s, right? And us we are given as step input. Yes, input, step input. Now can you find out the closed loop transfer function for this one? So it will be, so your gs will be ki by s plus 2. Okay, and your closed loop transfer function will be ki by s plus 2 plus ki. Okay, now you are providing a step input, so ys will be ki divided by ss plus 2 plus ki. So it will have the form ki by s square plus 2s plus ki. So for this one you will get a non-zero steady state is into ut step reference input. Okay, yes. Okay, for this one, if you do the partial fraction, what you will get? You will get something a by s plus some term over here, right? Okay, some term of s square plus something and something. So you can always design a ki such that, so this first term, if you are designing ki such that the response is stable, this term will have, it can have a structure of damped oscillation. The oscillation will reduce to 0. Okay, so at t tends to infinity, this term can go to 0, right? And what about this term? It will be just ut multiplied with some factor, but we have in our hand this ki. Okay, and we can design it as per our desire, and in that case this coefficient, which is this term which is in the numerator, can be 1, and 1 by s will have ut. So as t goes to infinity, this term, the right hand term, will go to 0 and we are left with ut only. Okay, then what will be the steady state error if the at time t equals to infinity, t tends to infinity, we are getting value 1? Then what is the steady state error if the step reference, if we are providing a step reference input? It is 0. Okay, so the statement that it would always lead to a non-zero steady state is not true. We can choose ki such that it can lead us to a zero steady state error. Okay, so this one is also false. Okay, what about the last one? So are you able to understand this one, the third option? Now tell me
No,
about,
ma'am.
okay. Okay, what I am saying is, you have a plant transfer function, right? You have something gs, okay? Then the response you will get will look something like that, right? Okay. Now
Yes, yes.
you can do the partial fraction of this one. Sorry. You can do the partial fraction of this one, then you will have terms like something ki by s plus some numerator divided by this term, okay? Now let's choose ki equals to 1. If you choose ki equals to 1, from the earlier concept, we will get the partial fraction, some value, it can be a by s, but it will depend on ki, okay? Plus some numerator will be there and it will have s square plus 2s plus ki, okay? And if we choose ki something greater than 0 and such that this numerator is equals to 1, then what will be the response of system? Yt will be ut plus some term which is stable, right? Because all the coefficients of this are non-zero and of same sign. So as t tends to infinity, this term will go to 0. So what will be left with? Ut. Okay. So the statement that we will have, because we are providing a step reference input and at t tends to infinity, we are getting the output as 1. Okay. So we are able, successfully we are able to track the reference. So the statement that we will have a non-zero steady state is not correct. We can have a zero steady state error. Okay.
Yes, ma'am.
Yes. And what about the last one? So in the last option, it is saying that the control input at an instant of time depends only on the current value of the error.
No, it also takes into consideration the past inputs.
Past value, yes, because it is integration, and integration depends on the
Summation of
past
all the
values, summation
past
of
values.
all the past and the present. So this option is also not correct. So which one of the following statements is false about a PD controller? Which one is false? So the controller transfer function is s into kd, right? Because this is, okay, it is a PD controller. So what will be the transfer function of a PD controller? It will be kp plus s into kd, okay? The first option is the controller transfer function introduces an open loop pole at 0.
False. No, it
Yes,
is false.
it is false because We have no poles here. Okay, we don't have any poles, so there is no pole at s equals to 0. So this one is false. What about second? It would provide a non-zero control input in the presence of non-zero error signal. Of course, if we have an error signal which is not zero, at least the proportional will give us kp into e which is not zero, right? So this option is true. It is anticipatory in nature. This one is correct or not?
Yes, ma'am, it is correct.
Yes, this is anticipatory means it has a predictive nature. So differentiation is nothing but a kind of a predictor, we can say. So it can anticipate the error. So it is also anticipatory in nature. So this is also true. And the controller transfer function introduces an open loop 0 on the real axis. So do we have any zeros here in the transfer function?
Yes, ma'am.
And what is that value?
Um, uh, minus Kp by Kd.
Minus kp by kd. And it is saying that it introduces an open loop 0 on the real axis. So kp is a real number, kd is a real number, so the fraction is also a real number. So yes, it introduces a 0 on the real axis. So this is also true. So the only false statement is the option A. Okay. So consider this second order system. Give a unity negative feedback and tell me which controller can stabilize the closed loop system. Proportional, proportional integral, integral, or proportional derivative. So the transfer of the plant is given as s square, sorry, s square plus 2. Okay. So what is the closed loop transfer function? Consider the controller as C. So it will be C by s square plus 2 divided by 1 plus C by s square plus 2. Because we have to identify the controller, so I have taken the generalized controller as C. Then you will get C plus s square plus 2. Now can you tell me what structure C should have so that we have uh, poles on the LHP? From here can you
Differential.
identify? Yes,
Differential controller.
but derivative is not in the option. We have with derivative
Then
proportional derivative,
proportional derivative.
and how you guessed it?
If we have s term in the denominator,
Yes, correct. That's the clue. If we look at the characteristic polynomial, we can observe that to have poles on the LHP, first we have all the coefficients non-zero, and here the coefficient of S is not present. And how can we introduce an S into the system? We can introduce using a derivative controller, right? So if C is something like KD into S, we will have S square plus 2 plus KD into S. Okay, and if we have KP also, then also no issue, right? So this will be our characteristic polynomial. So the controller that can stabilize this system is proportional derivative controller. Okay, now another question, we still have time. Okay, the steady state error of unity feedback system for unit step input is zero point 0.1. The steady state error of same system for pulse input RT, where RT is given as this function. Okay, so sorry, RT looks like this. So this time is 1 second and this value is 10. So the steady state error of a unity feedback system, if provided a step input, it was 0.1. Now I am changing the input, and now the input is RT, which is a pulse for 1 second, right? For 1 second I am providing 10 step value. Then what is the steady state error in this case? So from question, let's try to find out what information we are given. So we have a unity feedback system, means H equals to 1, right? So for steady state error, we know E steady state is given at as limit S tends to 0 S RS divided by 1 plus GH. In the previous question we have calculated, right? So this value we are given as 0.1, where our initial was step input. So S into 1 by S by 1 plus G, at S tends to 0, it is 0.1. Okay, so as S tends to 0, 1 plus G is what? 0.1. Okay, now we are changing the input. So how can we find out the transfer function of this input? Suppose you have step input ut, okay, and at t equals to 1 you have this input. If I denote it as 1 and 2, if you subtract 2 from 1, what you will get? You will get the same input as RT, right? If this is
Yes.
10 UT, okay, so this is UT, 10 UT, okay, and this is 10 times UT minus 1. We have shifted it by 1, so this is 10 UT minus 1. So RT we can write as 10 of UT minus UT minus 1. So what is the Laplace of this one? What will be RS? Will be 10 1 by S. What will the Laplace of U of t minus 1? If there is a delay, how will the Laplace change? So it will be e to the power minus s by s, okay? So we'll have 10 1 minus e to the power minus s by s. Now can you calculate the steady state error? We have the new input with the same system. Now can you calculate? So again, steady state error will be limit s tends to 0 SRS by 1 plus G. G is the same as it was previously. So limit s tends to 0 and RS is 10 by S 1 minus e to the power minus s and 1 plus G. Okay. So these s will cancel out. So limit s tends to 0, we have 10 into 1 minus. Now put s equals to 0. What you will get? If you put s equals to
0.
0, yes, if you put s equals to 0, you have 10 into 1 minus 1 and 1 plus g. 1 by 1 plus d, from here we will have at s tends to 0 will be 0.1. So what is the value? 1 minus 1 0, so it will be 0. So earlier with step input the error was 0.1. Now if I shifted the input by 1 second and scaled it by magnitude 10, the steady state error reduced to 0. Okay, so this is how uh, the response of a system changes. We can reduce the steady state error by changing the input only. Okay, one last question. So the unit step response of unity feedback system with open loop transfer function Gs equals to k by s plus 1 s plus 2 is shown. Find k. Okay, you have to find k, and the step response is like this. So this value is 0.75 and this is 1 second, this is 2 second. Okay, this is time and this is yt. This is the response of a system with unity feedback and step input whose open loop transfer function is k by s plus 1 s plus 2. Find out the value of k. How to calculate? So you are providing a step input, right? So the system should track the value 1. Unit step means it should be equal to 1 as t goes to infinity, but it is settling to which value? 0.75. So what is the steady state error? How much is the steady state error? 1 minus 0.75, it is 0.25. Now you have the steady state error. Now can you calculate the value of k? So first let's calculate the closed loop transfer function. So it is unity feedback system. So it will
In
just,
question they have given open loop transfer.
yes, this is open loop transfer function. That's why I am calculating the closed loop transfer function. Okay, from the open loop transfer
Hello.
function. Yes,
Directly we can use the formula of steady state error.
yes,
ESS is equal
but
to,
for
no
that
need to
we,
calculate the closed loop.
then how can we calculate the steady state error?
Okay. Steady state error formula is limit s tends to 0, S R of S divided by 1 plus GH.
Yes, yes, yes.
So a
So
open loop transfer function is given G. R of S is unit step response, that is 1 by S is
yes, yes,
given. Direct
yes,
steady
yes,
state error is given. From that
yes, yes,
we can calculate the value of K.
yes, yes. That only will, this way also we will land up to that only.
But there is
Yes,
no need to calculate. That's why I told
yes, yes,
closed
yes,
loop
yes,
course.
yes, 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 yes.
Okay.
So closed loop transfer function, if we calculate, we will get k by s plus 1, s plus 2 plus k. Okay. Now we know the um, as you said, we can directly calculate the steady state error as limit, like we have done in the previous questions. It is limit s tends to 0, SRS 1 plus G. Okay. So now can you calculate? So RS is nothing but step input. So it is 1 by S, and G is given S plus 1, S plus 2. Okay. So E steady state equals to limit S tends to 0. We will have S plus 1, S plus 2 divided by K plus S plus 1, S plus 2. What we will get? It will be 2 by K plus 2. And in the graph, we are given that from the graph, we know that the steady state error is 0.25. That is 1 by 4. So how much will be K?
six.
H 6.
6. Yes. So K will be 6 is the answer.
Mm.
And this formula I have shown you earlier how we can calculate how this formula is coming. Okay. From the block diagram, we calculate the closed loop transfer function, then we calculate r minus phi, and from there we got this one. So any questions? That's all for today. So we will meet next week to have some questions on Routh Hurwitz and other concepts. Okay. So thank you so much for today.
Thank you, ma'am.
Okay, bye.
Hello.